Hello everyone, this is Chuanhao Li, a PhD student from Beijing Institute of Technology. I'm very glad to share our recent work with you, exploring the effect of primitives for compositional generalization in vision and language. Compositional generalization is one of the fundamental properties of human cognition. An indispensable premise for improving compositional generalization is to understand the effect of primitives, including words, image regions, and video frames. Primitives are compositional building blocks mainly involved in vision and language tasks, and the determinants of sample semantics. However, existing methods cannot correctly establish the relationship between the primitives and the sample semantics, and thus the ground truth, so they can't achieve compositional generalization. In this paper, we present a self-supervised learning-based framework that equips existing vision and language methods with semantic equivariance and semantic invariance. Semantic equivariance means that the predictions of the methods should be equivariant with the sample semantics. Semantic invariance means that the methods should maintain the same predictions when irrelevant primitives are changed. To this end, we generate numerous labeled training samples, including equivariant samples and invariant samples, as shown in the figure. This is the overview of the proposed framework. We first estimate the effect of primitives in the query and video on ground truth. Based on the estimated effect, we generate invariant samples and equivariant samples. Afterwards, we randomly choose an invariant sample and an equivariant sample. Finally, we train the model with 3 types of samples by simultaneously minimizing 3 losses. We estimate the effect of primitives on ground truth and quantify them as numbers in the interval 0 to 1. For words, we estimate the effect based on their part-of-speech tags. For image regions, we compute the similarities between image regions and the keywords in questions to estimate the effect of image regions through the pre-trained clip model. For video frames, the frames within the ground truth boundary are assigned with a quantitative effect 1. For the frames outside the ground truth boundary, we compute the frame query similarities by the pre-trained TCL model. After the effect estimation of primitives, we generate numerous equivariant and invariant samples by masking different primitives in input. Equivariant samples are a series of samples that have different semantics from the original samples, and are generated by randomly masking primitives with high effect. Invariant samples are the samples that have same semantics from the original samples, and are generated by randomly masking primitives with low effect. We use 3 different losses to supervise the training process, including a method-specific loss, a self-supervised learning loss, and a contrastive learning loss. The method-specific loss is determined by the selected method, since different methods use different training losses. The main idea of the self-supervised learning loss is that the more the semantics of the samples are corrupted, the less the model can get the original ground truth. And the contrastive learning loss is used to pull up the predictions of original samples and their corresponding invariant samples, and push away the predictions of original samples and their corresponding equivariant samples. We apply the proposed framework to 2 tasks, temporal video grounding and visual question answering, to evaluate its effectiveness on the Sherra's CG, Clever, and Closer datasets. As shown in the tables, our framework improves the MSRD10 and GLT to outperform some advanced methods. Okay, in summary, we find that understanding the effect of primitives on ground truth can implicitly improve the compositional generalization capability. Then, the presented self-supervised learning framework can equip existing methods with semantic equivariance and semantic invariance. Finally, the proposed framework is capable of improving not only the compositional capability of existing methods, but also the IID generalization capability of them. That's all. Thank you.